In this video, we're going to look at the remainder and the factor theorem. And to do this, we're going to start off with a couple examples. The first example that we're going to look at is using synthetic division to divide the polynomial negative 3x squared plus 5x plus 4 by the binomial x minus 3. So again, we're going to use synthetic division. First, we need to put a number in what we call the box. The number that we need to put in the box is going to be the opposite of what is in our binomial here. So we're going to use positive 3. And then to fill in the rest of our coefficients, we're going to look at the polynomial that we're trying to divide. And we're going to take the negative 3, 5, and the 4 and put those coefficients in our synthetic division. Leave a space for us to write some numbers. And then our first step will always be to bring down our negative 3. And then from there, take 3 times negative 3, and that product will go underneath 5. So 3 times negative 3 is negative 9, and combine the 5 and the negative 9, we'll get negative 4. And then multiply again, 3 times negative 4, which will give us negative 12. Combine the 4 and the negative 12, which is negative 8. And what we remember from this is that the last number is always called the remainder. So the quotient that we get out of this, we would say is negative 3x minus 4 minus our remainder 8 over what we divided by, which was x minus 3. Let's take a look at another example. Evaluate a function. Let's use the same polynomial that we had in our division, negative 3x squared plus 5x plus 4, and let's evaluate the function at the value 3, which means we're going to plug in 3 for all the x's that we have in our function. So f of 3 looks something like this. Negative 3 times 3 squared plus 5 times 3 plus 4. We could go through our order of operations or type it into the calculator. The results that we're going to get, though, is negative 8. And here's what I want you to see. You see our remainder and our answer from the evaluation of the function? The results are exactly the same, and that's what gets us into the remainder theorem. What the remainder theorem says is that if we're given a polynomial, we're going to call that polynomial p of x, and we're going to divide it by some type of binomial, then the remainder is a constant called p of r, and this is what we see. P of x is equal to some other polynomial, call it q of x, times a binomial plus the constant p of r. Now I know that's probably not going to make a whole lot of sense to you, so I'm going to show you where this is useful and how we're going to apply it. Okay, the way that we're going to apply it here is let's evaluate a function. So we know that we can evaluate a function by plugging in 4 for all the x's, but let's show this a different way. Let's use synthetic division. Let's take the number that we're going to plug in, and let's put that in our box. Okay, so we know that we could do this, direct substitution. We could plug it in, go through our order of operations, and we could get 662. But again, let's do synthetic substitution instead. Put 4 in the box. Notice that when I do this, I'm not changing the value of the sign like I used to with normal synthetic division. Go ahead and take all of the coefficients that we have from our polynomial to write them. Make sure that all exponents are accounted for. So if we look at our polynomial here, we have a 4th degree polynomial. We need to account for the 4th power, the 3rd power, the 2nd power, the 1st power, and the constant. Well, we have the 4th power and the 3rd power. We do not have the x squared in there, so we have to put a placeholder of a 0 in there, and then 5 and the 2, and go through all of our steps with synthetic substitution. So we're dropping the 3, multiplying 4 and 3, which gives us 12, combining negative 2 and 12, gives us 10, multiplying 4 and the 10, get 40, adds to give us 40, multiply 4 and the 40 together, gives us 160, 5 and 160 gives us 165, 4 times the 165 is 660, and when we add the 2 and the 660 together, we get 662, so our remainder is going to be our answer. So the function evaluated at 4 is 662, so we can get the same answer for a function by simply doing synthetic division instead of direct substitution. Nowadays with our calculators and their strengths, we usually don't use synthetic substitution, but think way back when we didn't have a calculator at our disposal. We had to have another method, and I think doing synthetic substitution was probably a lot faster to do easy multiplication and addition as opposed to doing higher power multiplication. All right, let's try another one. Here's a function g of x, and we're going to want to evaluate at -1. Well, I'm going to take my number, -1. I'm going to put it in the box. I'm going to look at all of my powers that I have here. The highest power is the fifth power. I need all the coefficients for the fifth, the fourth power, the third power, second power, first power, and the constant, and borrowing their numbers. What you see here is we do not have a fourth power in our polynomial, and we also do not have the linear term, the x. So we put zeros in their placeholders. That's an extremely important part to this. Otherwise, you will not evaluate this correctly. Go through all of our steps with the synthetic substitution. Drop the first term, multiply the -1 and the 4 together. Gives us -4. Combine the 0 and the -4 to get -4. Multiply again. Combine. Multiply. Combine. Multiply. Combine once again, and then finally multiply. And -1 and -5 makes -6. So therefore, the function evaluated at -1 is equal to -6. Moving on. So we did the remainder theorem. How about the factor theorem? The factor theorem states that if a binomial, x minus r, is a factor of the polynomial p of x, if and only if p of r is equal to 0. In other words, if the remainder is 0 when you do synthetic substitution or synthetic division, then we know that the polynomial divides evenly. So that's pretty similar to whenever we used to do long division back in grade school. If a remainder ended up giving us 0, we knew that the two numbers would divide evenly. The same thing happens for polynomials. So a couple examples that we'll look at here. Can we determine if x minus 5 is a factor of the polynomial x cubed minus 7x squared plus 7x plus 15? And then we're going to find the remaining factors afterwards. So first we start with synthetic division. Now notice that this is not in function notation, so we do need to change the sign in our box. Borrow all of the coefficients from our polynomial, which are 1, -7, 7, and 15. Continue all of our steps with synthetic division by dropping the first term, multiplying 5 and the 1 together, combining, multiplying, combining, multiplying, and combining. And then notice that we have a remainder here of 0. That means that we know for a fact x minus 5 is going to be a factor of our original polynomial. But then we need to remember that these are all coefficients that in our what we call a depressed polynomial. If our highest power in our original polynomial was the third power, then our highest power of our depressed polynomial is going to be x squared. So our coefficients then are 1x squared minus 2x minus 3. We then need to figure out what are the factors that make up this polynomial, and that's where our AC method comes back into play. Okay, so then what we have here, the reason why I put this x minus 5 here is that we know that it's divided, so this times this would get us back to our original polynomial. Then we'll go with our AC method on the green factor here. 1 times -3. Can we think of two numbers that multiply to get -3, that if we were to add them, we're going to get -2? Those two numbers that you should be thinking of are -3 and +1. Now, if our leading coefficient of the x squared here is a 1, I can take these two factors and I can throw them back into the parentheses immediately. So the green parentheses, the two factors that make it up are x minus 3 and x plus 1. These are our two remaining factors that our directions are asking for. But those three factors all multiplied together are what would get us back to our original blue polynomial that we have above. Okay, so that's the use of our factor theorem. Okay, we're going to try one more example for this. Okay, so let's determine, is x minus 2 going to be a factor of our blue polynomial? And then let's find the remaining factors afterwards. Not in function notation, so we'll change the sign in our box. Borrow all the coefficients from our terms in our polynomial and go through our synthetic division steps by dropping 1, multiplying, combining, multiplying, combining, multiplying, And once again, we get a remainder of 0, so definitely x minus 2 is a factor of our polynomial. And then the coefficients 1, -5, and -6 are going to be part of this particular polynomial. Okay, and to remind you that we originally divided by x minus 2, we can multiply it by that polynomial. That gets us equivalent back to our original, the blue polynomial that I had above. And we're going to break apart the green polynomial with the AC method. So two numbers that multiply to give us -6, but if you add them, you get the middle number of -5. Those two numbers are going to be -6 and 1. Again, I have a leading coefficient of 1, so I can take the -6 and the +1 and throw them straight to my factors. So there's my two remaining factors. And if we were to go through and try to do a lot of FOILing and distributive property, x minus 2 times x minus 6 times x plus 1 would all multiply back out to give us the x cubed minus 7x squared plus 4x plus 12 that we have there. So there, in this